Hi everyone, we are going to pick up with 11.3 now, which is the first section that has a specific type of test to do on a series. And so the first of those tests to do is called the integral test. This test works a lot of the time. Not every test will work every single time, but the integral test works many times as long as you are really proficient in doing integral calculus. You will have to know how to integrate lots of different things. And so this is the first test. We'll start with looking at solving series, whether they converge or diverge using the integral test. So this is coming actually directly from, if you look through the improper integrals in Cal 2. So we're going to be doing a lot of things that are improper integrals. It is difficult to find the exact sum of a series. In most cases, you can never find the exact sum of a series. The best we could do is determine whether it converges or diverges, but not necessarily finding the sum. For instance, what we looked at in 11.2 was the geometric series. You can actually find a sum for that series, but that is a rarity. That is not the norm. So the integral test says, suppose you have a function that is continuous, positive, decreasing function from 1 to infinity. And then you have your sequence, a sub n, be the function that we're going to work with. Then the series from 1 to infinity of that sequence, a sub n, is convergent if and only if the improper integral converges. So basically, if the integral converges, so does the summation, or the other way around. If the integral diverges, so does the series. Like I said, this idea comes exactly from 7.8 in Cal 2. And the sum of the series is not the same thing as the value that you would get if you get a convergent integral. So just because the integral converges and you get a number, that does not mean that the summation sums up to that number. So they are two different ideas. But that's what we're looking for. One of the more popular ideas in doing this is what we call a p-series. You've seen the p-series already, if you remember from Cal 2 in that same 7.8 section. The p-series is named the p-series for the power, but it's not a power series because that's something else we'll talk about a little bit later on. But the p-series is a summation from 1 to infinity of 1 over n to the p, and it converges if p is greater than 1, and it diverges if it's less than or equal to 1. We saw this in the harmonic series in the last section, where we did 1 over n, that is the harmonic series, that diverges because your p here would have been 1, and if it's less than or equal to 1, it diverges. And so we already talked about that one a little bit already. The alternating harmonic series converges, but it does not use this rule here, so you have to be careful. And you have to go from 1 to infinity to apply this rule. Okay, so for example, let's use the integral test to determine whether the series is convergent or divergent. And notice it doesn't say to try to find the sum because most of these things we can't find the sum for anyway. So our a sub n would be n to the negative 3, or if you wanted to, you could write it as 1 over n cubed. It's the same thing. And so that's what our function is going to be. A function of n would be n to the negative 3. And so if I do the integral test, I would integrate this thing from 1 to infinity of n to the negative 3 dn, which is just a simple power rule, really. You're just going to end up adding 1 to the power. Uh-oh, I didn't add 1 to the power, did I? Add 1 to the power and divide by the power. So adding 1 to the power gives you negative 2 divided by negative 2. And we'll integrate that, or evaluate that, from 1 to infinity. I'm going to go ahead and move the negative 1/2 out in front and get 1 over n squared. And so I'm not really plugging an infinity in, but you can kind of look at it that way. What you're really doing is saying your n is getting bigger and bigger and bigger and bigger. And so since it's on the denominator of this fraction, the 1 over n squared, you're making the denominator bigger and bigger and bigger and bigger, which will make the overall fraction smaller and smaller and smaller. This part of the plugging stuff in will go to 0. And so all I'm left with is negative 1/2 times negative 1, which is positive 1/2. Now all the positive 1/2 tells you is that you got a number and that integral converges. And since the integral converges, then I know this series converges. So the integral converges, down here, which that means this series must converge as well. Now, like I was saying a while ago, this is also a p-series. If you rewrote this series as the summation from n equals 1 to infinity of 1 over n cubed, I could look at that and say, well, notice you have a power being 3. And since your power's equal to 3, which is greater than 1, I automatically know this series converges. By the p-series. So not only can you do the integral test, but you could also do a p-series representation of the series and then compare that to the powers and tell that it also converges. Hopefully that makes sense. Okay, this one's very similar. Use the integral test to determine whether the series converges or diverges. So in this case, we have the summation from 1 to infinity of n to the negative 0.3 power. And it works almost identical to the last one. Your a sub n would be n to the negative 0.3. And that would be what your function would be. And so if I wanted to do the integral test, I just integrate n to the negative 0.3 dn. And just like the last one, this is actually a power rule as well. And as a power rule, all I have to do is add 1 to the power and divide by the power. So if you add 1 to negative 0.3, you'll end up with 0.7 over 0.7 from 1 to infinity. And like I said before, with the 2 on the last one, I'm going to pull the 0.7 out in front. So I'm going to have 1 over 0.7. And then an n to the 0.7. If you plug numbers in, I'll get an infinity to the 0.7 minus 1 to the 0.7. Now, 1 to the 0.7 power is going to be just 1. So that part doesn't really matter. But you have an infinity to a positive power. That's going to get ever bigger and bigger and bigger and bigger. So this part right here is going to blow up. And subtracting a 1 from it or dividing by 0.7 is not going to deny that fact of it blowing up. So it's just going to keep getting bigger and bigger and bigger and bigger. This will go towards infinity. So this diverges. And that's the integral diverging, which means that back up here, this series must also diverge. You can also see this as a p-series if you would like. You could write this as the summation from n equals 1 to infinity of 1 over n to the 0.3. That 0.3 right there is your power. which this would be less than or equal to 1. Anything less than or equal to 1 makes that series diverge. So this diverges by the p-series comparison. So either way you would like to do it, both of them work. On your homework, what you'll notice is that you'll have a blank that just says converges or diverges, and you just have to pick which one it is. But you want to know make sure you know the reasoning behind why it converges or why it diverges. Okay, how about this one? If I want to do the integral test here, then my a sub n would be 2 over 5n minus 1. And that's my function. And so if I integrated that, I would have 2 over 5n minus 1 dn. And so you have to decide, how do you integrate that? Well, hopefully you all remember from Cal 2 that this is a natural log. I could move the 2 out in front, and to be a natural log, I have to have the derivative of the denominator sitting on top. So the derivative of the bottom is 5. So if I was to put a 5 up top and 5 by 5 out front, then the derivative of the bottom is sitting on top. And that makes this be a logarithm. And so this will just turn into the natural log of 5n minus 1 between 1 and infinity. Just like that. And then we plug stuff in. And usually what happens, if you end up with a natural log, you'll notice that it diverges. That's not 100%, but if you do end up with a natural log, a lot of the times they do diverge. And so if I plug the infinity in, I'll get the natural log of 5 times infinity minus 1. And remember, you're not technically plugging in infinity. Infinity is not a number. You're really just making a shorthand notation of you're plugging in massively large numbers. So on that infinity there, 5 times a massively large number is going to be really large. Subtracting 1 is not going to do a whole lot for you. But as you're getting bigger and bigger and bigger inside of a logarithm, your logarithm will also get bigger and bigger and bigger and bigger. So this entire logarithm right here is going to go towards infinity. The other logarithm, 5 times 1 is 5 minus 1 is 4. This part will go to the natural log of 4. But because that first part goes to infinity, this will diverge. And the integral is diverging, which implies that back up here, this series must diverge as well. So this is a divergent series. This is not a p-series, though, because a p-series is strictly a number divided by an n to a power, not a 5n minus 1. So you can't really do that. If it was 2 over 5n, yes, you could treat it as a p-series. Pull the 2/5 out in front of the summation and just have 1 over n. And we'll talk about how we can kind of use that fact to see that this can diverges in the next section, I believe. Okay, again, another problem, use the integral test to see if it converges or diverges. This one, kind of like the last one, will end up being a logarithm as well. Your a sub n is your n over the n squared plus 1. So your function is n over n squared plus 1. And so if I integrate from 1 to infinity of n over n squared plus 1. This is a logarithm. The derivative of the bottom would be 2n. So if I was to put a 2 on top and put a 1/2 out in front, then I have exactly the logarithm integral. This will turn into 1/2 times the natural log of the stuff on the bottom. Now in this case, I'm putting absolute values around the n squared plus 1, but they're actually not needed because you can't plug in a number from 1 to infinity in for the n to make that be anything but a positive number. So as we plug stuff in, this will turn into the natural log of infinity squared plus 1. And again, remember, it's really just massively large numbers that we're plugging in, minus the natural log of 1 squared plus 1. But we're going to run into the same issue that we had on the previous problem. If I take a massively large number and square it, it's large, plus 1 makes it even bigger. And the natural log going towards infinity, this will end up just getting bigger and bigger and bigger, going towards infinity. The other side becomes the natural log of 2, which doesn't really counteract the fact that the first part is blowing up to infinity. And so that means this thing has to diverge. And because the integral diverges, that means up here that the series has to diverge as well. And we would say that it diverges by the integral test. Okay, again, not a p-series because of the plus 1 on the bottom. So the integral test is pretty much what we would do here. Okay, how about one more? Use the integral test to determine if the series converges or diverges. And so here, my a sub n is the n squared e to the negative n cubed. And my f sub n would be the same thing. That's the function I'm going to use to integrate. And so I'll integrate from 1 to infinity, n squared e to the negative n cubed dn. In this case, you're actually looking at a little bit more complicated. The first ones that we've been doing have either been logarithms or power rules. This one's a u sub. And what I would have to do is let u be the negative n cubed. That way du becomes negative 3n squared. Pull the power down, subtract 1 from the power. Dn. I have the n squared, I just have to put a 3 in front and a 1/3 out in front of that, and then I have 3n squared du. These two together become my dn, become my du. And so I'll have a 1/3 times the integral of e. Oh, sorry, I left the negative off, didn't I? Du is negative 3n squared, so I have to put a negative on there. Hopefully that won't be too bad of an issue there. And then I'll have e to the u du. Now your limits on your integral would change as well. So if you want to change those, you could. If your n equals 1, then your u is negative 1 cubed, which is negative 1. So I'd have a negative 1 down here. And if my n was approaching infinity, then u would go to negative infinity cubed, which is negative infinity. Now, one thing you might notice is that your limits are upside down. Negative infinity is going towards the left. Negative 1 would be going to the right of negative infinity. So our limits are upside down, but I can fix that just by swapping the sign to a positive out in front, and that would fix it. And if you integrate e to the u, you don't even change it. It's just e to the u. And so I'm left with 1/3 times e to the negative infinity minus e to the negative 1. Now from Cal 2, hopefully you remember that e to a negative infinity, if your power keeps getting bigger and bigger and bigger in the negative direction on an exponential, this thing actually goes to 0. e to the negative 1 is just e to the negative 1, or 1 over e if you'd rather write it that way. So I'm just left with, if you want to write it as 1 over e, it would look like this. So this is negative 1 over 3e. Now, the fact that it came out to a number, because remember, e is just a number, says that it converges. So this interval converges. And since it converges, that means that this series is a convergent series. So your series converges by the integral test. Which would be your answer. So hopefully that's not too bad. I don't guess it is. And then also, you may also notice that you could have let u be n cubed instead of negative n cubed instead. And you would have also found out that it is a convergent as well.